Chapter 1 Fundamentals of Thermodynamics. Section 1.1 What is thermodynamics? Thermodynamics is the study of the transformation of energy and the behavior of matter on a macroscopic scale. What is a macroscopic object? A macroscopic object often contains many atoms or molecules. For example, 7-gram helium gas contains 10 to the power of 24 helium atoms. Even just 1 nanogram of water contains about 10 to the power of 14 atoms. So these two examples are macroscopic objects. If we study the transformation of energy and the behavior of this helium gas, or just 1 nanogram of water, it's thermodynamics. Conversely, quantum chemistry study only one or several atoms or molecules. That's called microscopic level. For example, we can study the vibration of one water molecule. We can study the energy of a water cluster that contains 2, 3, 4, or 10 water molecules. And that's quantum chemistry. We'll have to solve the Schrodinger equation for water molecule or 2 water molecules to get the energy and some other properties of individual water molecules. There's a bridge between quantum chemistry and thermodynamics. It's called statistical thermodynamics. So for example, if we study quantum behavior of one water molecule, we can use statistics to extrapolate the behavior of 1 mole water molecules. And we can also study the same system via 2 different methods: quantum mechanical and thermodynamic. The reason is, when we look at this diagram, this is the evaporation and condensation of helium. This is liquid helium, and we have moving helium atoms in the gas phase. We can either study the property of individual helium atoms, or we can use statistics to look at the collective behavior of many helium atoms in the gas phase and in the liquid phase. So we can study the same system using quantum mechanics or use thermodynamics. Again, there's a bridge between these 2 studies. The bridge is statistical thermodynamics. Again, thermodynamics is the study of the transformation of energy and the behavior of matter on a macroscopic scale. Whatever we study, it's the system. And the rest of the universe is the surroundings of the system. Between the system and the surroundings, there's a boundary. The boundary does not contain matter. The boundary does not contain any atoms, molecules, or particles. It's not a physical entity. The boundary is neither a part of the surroundings nor a part of the system. Now, we can tell the system plus its surroundings is equal to the entire universe because of the definition of the surroundings. Again, the definition of the surroundings is the rest of the universe. So if we look at some thermodynamic properties such as heat or work, we have these 2 equations. The heat flows into the system plus the heat flows into the surroundings is equal to the heat that flows into the universe. We're going to assume the universe is an isolated system, so heat does not flow into or out of the universe. Therefore, Q sub universe should be 0. And therefore, we have Q system plus Q surroundings is equal to 0. Similarly, the work done on the system plus the work done on the surroundings is equal to the work done on the entire universe, and that has to be 0. There are 3 different kinds of systems: open system, closed system, and isolated system. What are the differences? We look at 2 important features. We look at if there's any matter exchange between the system and its surroundings. We look at if there's any energy transfer between the system and its surroundings. An open system may have matter exchange and energy transfer with the surroundings. For a closed system, there's no matter exchange, but it's possible to have energy transfer. For isolated system, there's neither matter exchange nor energy transfer. We're going to study many thermodynamic properties in this class. For example, pressure P, temperature T, volume V, entropy S, and also internal energy U, enthalpy H, Gibbs free energy G, and Helmholtz free energy A. We will also study heat capacity, chemical potential, denoted by mu here, in thermodynamics. And those thermodynamic properties or functions, they depend on each other. For example, enthalpy H is defined to be U plus PV. Helmholtz free energy, or simply Helmholtz energy, is defined to be U minus Ts. Gibbs energy is defined to be enthalpy minus Ts, temperature times entropy. Again, this is just the definition of the Gibbs energy or Gibbs free energy. And we know H is U plus PV, and also we know A is U minus Ts. So we can have some other equations. The changes in this thermodynamic properties of a system are always governed by the laws of thermodynamics. In sections 2, 3, 4, and 5, we will introduce the zeroth law, first law, second law, and third law of thermodynamics.